This is Chapter 12, Renewable Energy and Nuclear Power. So an overview of Chapter 12, we're going to cover direct solar energy, indirect solar energy, other renewable energy sources, and nuclear energy. So what is direct solar energy? Well, we know the sun produces a tremendous amount of energy, of which only a small portion reaches the earth. And solar energy differs from fossil fuel nuclear fuels in that it is perpetually available. It is dispersed all over the Earth's surface, but it's more concentrated in some areas than others, right? And it's also, this is how the sun's energy is dependent on the latitude, season, time of day, and cloud cover. So you can see how much solar energy is distributed along different parts of the United States. In this diagram, we know that in the American Southwest region, it gets more solar energy, and then it decreases as you go up in latitude and you move eastward. Well, there are two types of solar energy, right? There's passive and there's active. Passive solar energy basically means that it's a system of putting the sun's energy to use without requiring mechanical devices to distribute that collected heat. When we think of passive solar heating, we think mostly of like things that can be built without requiring turbines, generators, or diffusers. And a great example that you see in this picture right here is an adobe home in the southwestern US. It's been used for centuries and uses materials found naturally to kind of insulate and keep the cool inside. Thick walls are carefully placed as well as windows in certain regions. And here you can see those design features that contribute to passive solar energy heating. In modern times, we have the solar sun space. It utilizes the solar energy to heat and cool homes through different types of pipes, insulated windows, etc. And it can be added to existing homes. Active solar energy is as a system of putting the sun's energy to use, in which a series of collectors absorb the solar energy and pump or fans distribute the collected heat. In this example here, we see a solar collector box on the roof of a building, and then the solar panel box is a box with a black metal base and a glass covering that then allows for heat exchange into a storage tank or into a pump, which can then heat water or cool it down depending on what it's used for. And unfortunately, only 8% of energy in the US is used this way to heat water, even though it should be more. Solar thermal electricity generation. This is something that you guys have probably heard of, and that is electricity produced in several different ways by using mirrors or lenses that concentrate the sun to either heat either a fluid-filled pipe or another mechanism. So I'm going to explain it. You have a curved panel, right, that collects sun into that little pipe, which then heats up the water, which then it is moved, water or oil, which then has energy to be moved, and then it can be produces electricity. It's more efficient than other solar technologies. It has no air pollution and no contribution to global warming or acid precipitation. The photovoltaic solar cells, and it's a method of converting sunlight to electricity using layers of materials that either readily absorb or give up electrons. It has no pollution and minimal maintenance. These are solar cells. They currently provide more than 21,000 megawatts of electricity worldwide. and that's about the same as 21 large nuclear power plants, but this is only 0.7% of global electricity. These solar cells are also not very efficient. They only convert about 15 to 18% of solar energy to electricity. However, they can be incorporated into building materials like you see here and how I mentioned in chapter 11's LEED building certification. Indirect solar energy. This is basically biomass, wind energy, or hydropower. It's any collection of energy that isn't directly producing electricity. So it's basically stored elsewhere, or it's kind of like a side effect of it, right, to produce the energy. So we talked about biomass in chapter 10 and its plant materials such as wood, crop waste, and animal waste. Wind energy is electric or mechanical energy obtained from surface air currents caused by solar warming of air. Hydropower is a form of renewable energy reliant on flowing or falling water to generate mechanical energy or electricity. The energy from biomass is contained via photosynthesizing plants. It's the oldest known fuel to humans, and it's still used by half of the world's population, primarily low-income, lesser developed nations still use it. It's renewable when it can be used no faster than it can be produced. Okay? That's the only time it's renewable. However, what we have seen is that through deforestation, it becomes a non-renewable resource. And it can be converted to biogas or liquid. There are several advantages and disadvantages to biomass. It reduces dependence on fossil fuels. It often uses waste materials. And if trees are planted, it's a no net increase in atmospheric CO2. However, the disadvantages of biomass usually outweigh the advantages. It requires a lot of land, water, and fossil fuel energy, so a lot of resource input from other things. It can result in bad air quality because you're burning basically stored carbon, plant material, obviously a lot of smoke. It's highly inefficient because a lot of it is released as heat, and it can lead to deforestation, desertification, and solar erosion, as I had mentioned. Wind energy. The wind energy capacity has increased from 20% to 45% in the last 10 years, and that's because of more countries, cities, regions, municipalities demanding wind energy. It's caused by the heating of Earth's surface, and thus it's an indirect form of solar energy. Radiant energy from the sun is transformed into mechanical energy, which then moves air molecules. Wind is sporadic over much of the Earth's surface, varying in direction and magnitude. New wind turbines can be huge, almost 100 meters tall, and have long blades designed to harness wind energy efficiently. As turbines have become larger, more efficient, cost for wind power has declined rapidly from 0.40 per kilowatt hour to 0.03 to 0.08 per kilowatt hour. So it's becoming more prevalent. It has few environmental problems. Some of the most poignant are killing aerial wildlife, and that it's kind of like an eyesore. A lot of people don't really like seeing them in their backyards or like near their homes. It's just a bunch of windmills, and it can kind of be a waste of land. As you see here, it does mean you need to set aside large amounts of land for it. But I think the benefits outweigh that. It's a no waste clean source of energy. Hydropower is the most efficient energy source, and it's the most widely used renewable energy source. Basically, the sun's energy drives the hydraulic cycle, which encompasses precipitation, evaporation from land and water, transpiration from plants, and drainage and runoff. As water flows from higher elevations, remember when we talked about streams and rivers, back to sea level, we can harness its energy through installing turbines and dams. Traditional hydropower, it was only suitable to large dams. New technology allows for low flow, smaller streams to be dammed and still produce electricity. There are a lot of advantages and disadvantages of dams. In my opinion, the disadvantages outweigh the advantages. It causes a lot of ecological disruption in both the downstream, upstream, and the reservoir. And you can see here, it displaces people. There's a lot of loss of cultural resources. So just read these over, pause. They're pretty self-explanatory, and if you need more information, look into your book. There are other renewable energy resources, geothermal energy, energy from the Earth's interior for either space heating or generation of electricity. And tidal energy is a form of renewable energy that relies on the ebb and flow of the tides to generate electricity. It's similar to hydropower, in which a dam across a bay allows for a turbine to spin, allows for the tides to spin a turbine that then produces electricity. But it is location dependent, obviously, because not everywhere has high tidal energy potential. Geothermal energy is an enormous energy source. 1% of the heat in the upper 10 kilometer of the Earth's crust is equal to 500 times the Earth's fossil fuel sources. And hydrothermal energy reservoirs, which are created by volcanoes, allow for heated water near volcanoes, which have steam, to also spin turbines and create electricity, as you can see here. Geothermal heat pumps, such as this, which are seen all throughout Iceland and highly volcanic activity areas, basically means that there are these long pipes running deep into the ground, which are heated at different temperatures, and then the water is, containing more active energy, heat, and then it's pumped back up into an office building. Nuclear energy. Nuclear energy is very controversial and very interesting. In 1905, Albert Einstein hypothesized that mass and energy are related in his famous equation E equals mc squared, right? This suggested that nuclear reactions in which matter is converted to energy have the potential to release a vast amount of heat. Over time, we have discovered that this is nuclear energy, and it's released by nuclear fission or fusion. Nuclear fission is the splitting of atomic nucleus into two smaller fragments, which is accompanied by the release of a large amount of energy. Nuclear fusion is joining two lightweight atomic nuclei into a single heavier nucleus, accompanied by the release of a large amount of energy. Know these two terms, know their differences. Joining, fusion. Splitting, fission. Radiation is the energy in the form of electromagnetic waves or high-velocity subatomic particles. Here's how nuclear fission happens, which is what we usually see in nuclear power plants. Starting at the left side of the figure, we have a neutron bombarding a uranium-235 ion, which then causes these atomic fragments, and from that there's energy. This continues happening until more fragments come out, and the cycle continues on in a chain reaction. This is what's happening in a nuclear power plant. A nuclear reactor is the device that initiates and maintains a controlled nuclear fission chain reaction to produce energy. These little things right here, these little black things, are the actual uranium dioxide pellets. They contain about 3% uranium-235 isotopes, which are the ones that are bombarded by neutrons to release energy. And these uranium pellets are loaded into the long fuel rods, which are grouped into square fuel assemblies and then used in the nuclear reactor. Here is a very simplistic diagram of how nuclear reactions produce electricity. You have the control rod where the reaction occurs. There is water running through these tubes. It heats up the water, right? I'm sorry, no. There is the heat exchange and the heat and the energy that comes off from the nuclear reaction, which heats the water right here. Then that water becomes steam, which then powers the engine turbine. And then you get that steam powers the electric generator, and that's how you get electricity. The water then goes into the condenser and then can be reused. So it can be a closed process. Here is a side-by-side comparison of coal and nuclear in terms of land use, daily fuel requirement. As you can see, land use is significantly less because you just have a power plant. Coal, you need to take into account the mining of it. Daily fuel requirement is very low as well for nuclear compared to coal. However, the radioactive emissions are obviously a lot higher for nuclear than coal. And the problem with this is that it takes thousands of years for these radioactive nuclear waste products to become safe to handle without, long-term impacts on human health. Safety issues in nuclear power plants. There could be meltdowns at high temperatures. The metal encasing the uranium fuel can melt, releasing radiation. However, since the 1980s, probability of meltdown is very low. But due to 3 major incidents worldwide, the public perception is that nuclear power is not safe, even though it's pretty safe compared to the coal killing so many people. However, because of media sensationalization of these 3 events, if you ask people, they do not want nuclear power. Let's look at one of these cases, Chernobyl. It happened in the 1980s in the Soviet Union in northwestern Ukraine on the border with Belarus, which was also part of the Soviet Union. Over the course of 3 days, 170,000 people had to abandon their homes. The fallout was extensive because the Soviet government did not have the proper resources to contain the radiation, as well as they did not alert the rest of the world appropriately so that they could get those resources in time. What we have seen is the long-term effects because there was a frequency of birth defects and mental disabilities increase over decades, and a lot of children as well as adults suffered leukemia, cancer, and other abnormalities to their immune systems. And you can see here in this little picture the radioactive immediate fallout from Chernobyl, which extended all throughout Europe. So when we talk about radioactive waste, there are 2 types, low level and high level. This in low level is like glassware, tools, papers that give a low amounts of ionizing radiation. And it happens all the time in power plants, research labs, hospitals, and industry. States are responsible for all the waste they generate. And there are 4 sites, Washington State, South Carolina, Nevada, and Utah, that currently store most of the country's low-level radioactive waste. High-level radioactive waste, such as liquids, gases, and solids that give off large amounts of ionizing radiation, come from spent fuel rods and assemblies from nuclear power plants. They have to be stored in very high technology, high security facilities. Here are some of the temporary storage solutions that the United States has. However, there is no below ground storage in the US as of 2017. And that has become a huge problem. When a nuclear power plant is closed, it undergoes something called decommissioning. And there are 3 steps to it: storage, entombment, and decommissioning. Well, there are 3 solutions to it. Storage, as the name states, is that the utility company has to guard the power plant for 50 to 100 years as some of the materials decay, making it safer to dismantle the plant later. Entombment, which basically means encasing the entire power plant in concrete, allows for the radioactivity to remain intact for at least 10,000 years. Sorry, 1,000 years. However, accidental leaks happen all the time, and so it cannot be guaranteed for a lot of future, for a long future. And the third option, which is decommissioning, which is dismantling the power plant immediately after it closes, means that robotics can make it feasible to tear down sections of old plants that are too hot for workers to safely dismantle it. However, it is the most expensive option, but it is the best. As of 2016, there are 141 plants retiring. Currently, there were, before 2016, there were 31 retired plants, and the rest of the plants are aging at an increasingly fast rate. So in the next 50 years, we're going to see a lot more nuclear power plants being decommissioned. Storing nuclear waste. In 1982, the nuclear waste policy required the government to own all nuclear waste that could not be handled by entities appropriately. Yucca Mountain has been identified in Nevada as the only candidate for underground storage of high-level radioactive waste. It could take 42,000 plus tons of spent fuel produced in the US to date, plus more that would be produced until about 2025. However, a lot of people don't want it to happen, so it hasn't. Current active storage has not occurred, but here is what it would look like for it to be remotely stored. Now, the reason why Yucca Mountain was chosen was because of the geology. It does not have a lot of geologic activity, right? The remote possibility of a volcanic eruption 1 in 10,000 years. It's not very near active fault lines or a water table, so that's why they chose it. But it's still not been approved by the government because of the fear by surrounding states and politicians about the fallout if the nuclear waste was to get, exposed to the environment. So we haven't seen very much progress on that. That's all for this chapter. Please email me if you have any questions. Thanks.